Good morning, everybody. I'm back again. This is Dr. Nandi. Today we are going to talk about Wilcoxon sign rank test for one sample. So without further ado, I'll share my screen with you. So this is the problem on Wilcoxon sign rank test for one sample. First of all, I want to tell you this sign rank test is a non-parametric test. That means we do not assume that the samples came from a normal population. So the problem states use the Wilcoxon sign rank test and alpha equal to 0.05 to test whether the population median could be greater than 37 from the following sample observations. Okay, so these are the observations 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 samples. Okay, so first column, I write down all the observations. Then the next column. So your null hypothesis is MD, median is equal to 37, alternate median greater than 37. Okay. And the second column is called the difference column. It is XI, means each individual observation minus the hypothesized median of 37. So for example, for the first observation point, 34.6 minus 37 is minus 2.4. And I do it for all the 14 samples, okay? Next, I convert these differences into, uh, absolute differences. Notice the two vertical lines around DI in the third column heading. That means the negative differences will become positive, okay, because I'm doing the absolute differences. Remove the negative sign. Then I rank these differences starting from the lowest one to the highest one. For example, 0.9 in the absolute DI column is the lowest difference. So its rating is number 1. Next one in the list is 2.1. Its ranking is 2. Okay. Next one is 2.4. Its ranking is 3. Okay. And the next one is 2.5, ranking is 4. Okay. Now, next one is 3, its ranking is 5. Now there are 3.2. These would have normally taken 6 and 7. So I take 6 plus 7 is 13 divided by 2, 6.5 as the ranking for each 3.2. So there, because there are 3.2, the two next two ranking 6 and 7, I add them up, divide by 2, 13 divided by 2 is 6.5. Okay, this is the way we do it when uh, difference is repeated. We take the average. So 6 and 7 are gone. Next one will be 8, and that is 4.4, and so forth. Okay. Next, I separate the ranks into R plus and R minus. That is, the differences which were originally negative. For example, the first one, minus 2.4, originally negative. Its rank will be placed under R minus, the last column heading R minus. Is because it is negative, is ranking 3 is under that column. Similarly, the ranking for negative 3.2 is in the under the negative R minus 6.5, and ranking for minus 0.9, which is 1, is also under R minus. Then I separate into two columns, R minus and R plus. All the positive differences are whose ranks are reproduced under R plus. So negative differences, their ranks go under R minus column. Positive differences, their rank go under R plus column. Then I add up the sum of the ranks. Okay. Now, the sum of the positive ranks is 94.5. Sum of the negative ranks is 10.5. Always use the lowest sum of the ranks as the test statistic. So test statistic W comes from the Wilcoxon sign rank test. W is sum of the R minus, the lowest sum of the ranks is 10.5. Now I say look up table for critical values of Wilcoxon sign rank test, lower and upper critical values. When n is 14, Remember, our test is a right tail test, alternate median greater than 37. So we look up for one tail test, okay? And for alpha equal to 0.05, critical values are 26 and 79. I'll show you the table at the end of this problem. And for alpha equal to 0.005, the critical values are 13 and 92. Since test statistic W is equal to 10.5 is less than upper critical value for alpha equal to 0.005. Why do we focus on upper critical value? This is because we have a right tail test, alternate hypothesis MD greater than 37. So we focus for alpha equal to 0.005, up the highest critical value is 92. Since test statistic W is 10.5 is less than the upper critical value for alpha is equal to 0.005 as well as for alpha equal to 0.05, decision is reject 80. And p value is definitely less than 0.005. Okay, because even for p is equal to alpha equal to 0.005, the critical values in 13 and 92, our test statistic is only 10.5. Okay, so how does the table look? Let's take a look at the table. This is the table. Sorry, it is in a side by side view, but if you focus on the first column, which is n equal to 14, okay, n equal to 14 is the sample size. So you draw a horizontal line through n equal to 14, and then you go to one tail test, alpha is equal to 0.05. What is it? It is 26 and 79. And if you go to the last column for single one tail test on the top row, 0.005, it is what is it? It is 13 and 92 for n equal to 14. So we're looking for, first you look at the one tail test, look at the alpha value in the top row for one tail test 0.05, and n equal to 14, draw horizontal line where they intersect are the two critical values. For alpha is equal to 0.05 for one tail test. Also you can look up for alpha is equal to 0.005, n equal to 14, uh, n equal to 14, the critical values for right tail test, for one tail test. Yeah, as we discussed in this problem, in both the cases, the test statistic is less than the upper critical value. Why are we interested in the upper critical value? Because this is a right tail test. If it had been a left tail test, then we would have been interested in the lower critical value. Anyways, we reject the null hypothesis because the test statistic is less than the upper critical value. If you have any question, please do not hesitate to write a comment and I'll get back to you as soon as possible. Thanks for watching. Please subscribe to my channel. I come back almost every week with different problems. Take care and have a nice day, and I will see you next time. Okay.